the time I got really tired at the seating meeting.
That part's kind of easy.
No. When you were sewing. I think it was close to 10K.
Not bad. Mine's only about.
Well, yes, but I pulled the tool and I was trying to get the system working.
I did like how we pre-packed the launch and like made sure everything.
It was nice when we got to the launch.
I was trying to do
It's like when we got to see we integrated almost everything. All we had to do was like the last final touch.
Thanks, Ray.
Nice.
Simply did not know.
What?
There's an issue with the
Yeah, no, it's serious. So you click like a journal, like it comes up and the entire thing is
You can't even like read it. I'm probably gonna take that. It's on tie-in. Yeah, is it reserved?
great.
Man, you gotta get on that Navy SEAL time schedule, you know what I'm saying? No. Wake up at 4. Don't pass. Wake up at 4, go for 3-mile runs every
Oh, how was
Yeah, go around the lab is pretty cool.
I like running.
It's just well, it's just like, it's one of those things you have to have conditioning.
Yeah.
It's like, the more you run, the more shit is going to use. Yeah, you just have to start.
But it's because like the group I was in, like.
Really?
I mean, I kind of thought you were gonna forget it.
Well, I did forget, but I don't think so.
Oh yeah, you're supposed to be here.
I think so. Yeah, I thought here.
This is my third cup of coffee today.
Well, it's just the same.
I mean,
So like, forward, shoot back around.
Oh, you got the spoon. Yeah. No, nobody can sit in this table. No. I was like, the spoon.
You know what? I don't have
He's the rookie pro.
there's options over here. I didn't think about that.
What?
I thought you read one.
Yeah.
Well, they're all
Yeah, you gotta eat better. It is. It's really, really worked out. Now I have all my mutants. So I yeah.
Just for.
I mean, when you're living on campus, you don't really have.
I don't know it. How are you?
It's what it is.
I'm good. I'm glad to see you made it.
On campus, they have like enough stuff to like good stuff for you.
Oh, cool. Pay for the whole thing. Honestly, it's just really yeah, there's donuts. Feel free to grab food, like make yourself at home.
Like on this project,
There's an acid.
stuff because like it's going like Sundays. I got a zero. Like this. Alright.
Just a lot. Yeah.
Off
Yeah.
like
Recovery.
that's like going to a
Oh really? Yeah. You have to do something in person here or training.
So, residential.
So I've been doing that. Well, I'm glad you stopped by so we can all see.
I get paid to honestly do my homework.
I'll be back. I think
I'll be done on this.
just next to you.
Not too PhD.
Also, like, I'm also
Okay, so we really, that'd be the exact same point. So finishing my master's this semester.
instructional.
I thought about like a half second ago, requirements. I was like, I can't do this. Like, not right now. Not right now. I was like, I can't do this. I'm actually working on it now. I'm interviewing at 10X on Tuesday. So, yes, yeah, I know. Yeah, it's okay. But they were also for radar positions, so I tried so hard to get space division. I was like, hey, he was like talking to like,
Yeah, exactly. Because it's not like you don't have like whole.
I literally sent them an email. I was like,
I have they.
oh, I sent it to Nick and like one of the other guys. It's like, it's just like he wants out.
Yeah. Yeah.
So I got right on.
Mark literally refer that.
So I'm doing that, and then actually that's on Tuesday. On Thursday, I should be getting it. Unless Lockheed. I mean, because I don't really want to make this. I'm just taking this.
Alright,
Got the job.
that would actually be awesome.
Hey, Jack. By any chance have your charger? You do?
So charger now.
Laptop.
No, but I feel pretty good about that. So it's just 'cause, like I have really.
I think I'll be okay. I think I'll be okay.
Oh yeah.
My laptop's battery lasts
Yeah,
for like 10 hours.
Tuesday, Thursday, I have class.
Not live streaming
Basically
necessarily,
10 to
but
5.
you also have the digital version of it.
So like those days are rough. But, like Monday, Wednesday, Friday, my latest class. So like Monday, my only class day.
I don't know. They just watch it in chat.
Did she fix the link in the Bobby just did some weird FaceTime thing. I don't know what he did.
You can't respond on your phone?
I guess.
I don't know what kind of donut this is, but I'm gonna eat it.
Make it like a nature documentary.
Really? Like 11:30. Seems like a donut to me. One break in there. Not to break in the 3 class. It's just a basic like. Wow.
That's awful.
That's a lot.
I wish I could see.
Yeah.
What do you do at school?
Yeah.
I wonder if he's coming here.
They're coming. Unless they're
I will be a
unless they're usually just like rocking boys.
Hi, how's it going?
She's like, just enjoying the coffee. He was really excited. Like, he was so enthusiastic about it. He was like,
I'm already ready for this semester, and
it's like,
I know, I do that all the time.
what?
Yeah.
2 times this semester, I'm gonna have 2 midterms in one class.
Yeah, I know.
You want to be that person?
Actually,
It's nice seeing you.
all of them except one midterm. It's like it's 14 credits.
I'd be like, let me split it with you so you don't technically.
I've texted him a few times about DCS, and that's it.
On the website. BSLI.space. Scroll down.
That is true. Are you going to really wait that long for them to do
That's
that?
from me too.
Yeah, that's.
I know, it does feel like
small
work.
piece left.
I did a bunch of these tutorials, and it's really satisfying in a lot of ways, but also way more work than almost any other video game I've ever played.
They will memorize how to.
Yeah,
Yeah, that's not bad.
Be nice to the Senate.
it's the Senate person.
Actually, it's the House representative.
Oh, the woman that's visiting?
Were you at the meeting Sunday?
I remember that from AP US History.
Nobody, you know.
State issue. I'm pretty sure
Oh,
the
he
whips
didn't
are in
have
charge
anything
of
to
making
do
sure that
outside.
they go in line with the
We were voting for instance.
That seems to be what I
There's just so much that goes on in the government. Honestly, after.
Right. Sorry, buddy. Can't have you. I know we already take that back.
It's like you have the mail thing planned.
when you send out information to the status, it gets chaotic.
Oh,
Like your mailing CMA is there to essentially
and now once that's like they get it, off of the IR, you're doing it on your phone. By the time you get it, it's like a month.
so everything. And so like Air Force is like, oh, no, actually, I also do. So it's just like this
It was like they're behind schedule. So it's like this.
So you have all these voices of like reviewers. You don't want to deal with the RFS. It's just like Navy wants this new ship. Air Force wants this new plane. They send up their stuff, and everyone likes to make their capabilities.
Once you get results.
So you make informed recommendations to decision makers about what to put in.
And I got put in here.
Not
And I
necessarily
forgot until like today to like switch my schedule.
So it's like
Which like
do like one
only
step
the second week
before
lessons.
recommendation.
You want to add a class,
Here's
get
what
that.
it is, not necessarily what I think we should do
But
about
I
it.
emailed my advisor, so I got a so I emailed Dan Farr and I was like, hey, I was stupid.
That sounds
Take permission.
Right.
Probably did.
so there has to be a really good reason why I would even suggest that.
It sounds like you can vary a lot between like being really interesting.
Can you just give this to me? At the right name. Oh, Hi everyone. I'd like to thank all of you for coming out to our critical design review tonight. I especially would like to thank any industry professionals or professors who are either live streaming this right now or in the audience. Any comments you give to us really helps our club and helps us further our knowledge in rocketry. I also would like to give a special thanks to the many sponsors of BSLI. Mike Snyder from Made in Space, Huntington, Arconic, Advanced Circuits, Gateworks, the Ohio State Grant Consortium, Department of Engineering here at OSU, of course, and then any alumni donors that we've had. To begin our design review, I'm going to give a quick overview of what to expect for our entire presentation tonight. So essentially, me and the Deputy Project Manager, Avi, we're going to give basically an introduction about what Spaceport, what our team is, what our goals are for the year, etc. And then we have each of our sub-teams will each give up separate presentations about what their sub-team's purpose are, their requirements, what the design is, any risks that they see from their designs, and ways to mitigate those risks. So, what is the purpose of Spaceport? So here at BSLI, we have multiple project teams. Spaceport, of course, is one of them. So, one of our main goals that we strive to do every year is compete in the Spaceport America Cup competition, which is held every year in New Mexico. So this competition is pretty special because it is the world's largest intercollegiate rocketry competition. Around, I think, 200 teams are accepted this year, and there's a multitude of categories you can compete in. And just as a background reference, for those acronyms, SRAD stands for Student Researched and Developed, and then COP stands for Commercial Off the Shelf. And these usually refer to the type of propulsion we use, so there are many different categories, and the one we always strive to compete in is the 30K SRAD category, which means we strive to have a rocket that's capable of reaching 30,000 feet, while at the same time having a student research and designed solid motor. One too many. Okay, so what are some overall project goals that we have this year? One of the biggest things, of course, is to be successful in our 30K SRAD category. And to do this, essentially, we need to conform to Ezra's rules on design. So Ezra has many requirements for their design, which is most of them in part to keep us safe and also just to make the competition a little bit more challenging. Like one such requirement would be like a payload minimum weight, etc. Another main goal that we do have, this is kind of personal to our team, is to have the majority of the rocket composed of SRAD parts. So this is not a necessity if you're competing in the SRAD category, but we like to do this just because it's much more satisfying to, say, like build a nose cone from scratch than to buy one, and then see it fly and work and not like fall apart at 30,000 feet. Another main goal that we have is, of course, to perform tasks while staying safe. We haven't had any accidents on this team, and we want to keep it this way. So, of course, safety is definitely a top priority of ours, especially when dealing with some of these dangerous like power tools and machines, even like stuff with the propellants. And then finally, another really large goal is to continue promoting inclusive club culture. Rocketry is fantastic. Of course, like none of the leads would be here if they didn't think this. And we definitely don't want to make this only available to like any certain type of people of any like, we want to make it open to anyone, essentially. So now I'm going to go over basically the entire rocket design for this year. So essentially, this design has not changed much compared to 2 years ago. It has a bit from last year. So our recovery system is going to be located mainly in the nose cone and partially shared by a few inches in the body tube, where we'll have our recovery bulkhead at the top part of the body tube. Then we have something new this year called our systems bay. Essentially, this is just going to be a combination of payload and avionics, but they're going to be shared on one combined structure. And the goal of this is to make the integration of our rocket easier. And then, of course, you have the propulsion system all the way down here. And you can kind of see from the colors just what the parts are made of, that we'll have our own created nose cone out of carbon fiber, and then a body tube out of carbon fiber. Then a fiber, this is our team's special like transition section. And this will be made out of fiberglass to ensure that we have radio frequency transparency, because this is also where our telemetry will be housed. And that's a very light overview. Of course, our leads will go into much greater detail about all of these. Oh, gosh. Okay, now I'm going to hand over to Avi, our deputy PM, to continue giving the introduction.
Thank you, Anu. So, like she said, my name is Avi. I'm Deputy Project Manager for the Spaceport team. So first, I'm going to go over the project design motivation. So last year, we had a minor issue where the motor exploded, essentially, and the rocket only got to about 360 feet. But on the plus side, we drastically improved integration. So something that we're going to try and do this year is continue with the improved integration, but we're going to focus a lot on making sure we do full-scale motor tests so that we can avoid any kind of problems with the motor like we had last year. And then, of course, we'll be continuing to develop all the individual subsystems as we always do. So this is a quick overview of the team structure. So you can see the project manager up there interfaces with all of the sub-team leads, and then she also interfaces with myself doing administrative stuff while doing the technical stuff with the leads. So I'm going to now hand it over to Carly to do structures.
Okay. Hi, I'm Carly. I'm the structures team lead. So the purpose of the structures team is to construct the airframe and all the internal components, mostly so that they survive all the stages of flight, but also to optimize the vehicle's performance in flight. We also provide hands-on opportunities for all of our members to construct composite components. And we also build the team's information base and pass on information so that future iterations of the team can use it. The project requirements for the structures team are to, firstly, withstand any loads the vehicle may experience in flight. Integration should remain simple and straightforward and take less than a few hours. We're aiming to launch on the first day again like we did last year. The airframe should be manufactured precisely enough to reflect the aerodynamics team's work predicting how it will perform in flight. And our materials should be light enough so that our vehicle can get to 30,000 feet while still maintaining that strength. On our materials, we did some composite testing at Scott Lab according to ASTM standards. The pieces varied in number of layers. We did 2, 4, 6, 8, or 10 layers, and they varied in epoxy type, high or low temperature. In some of our layup processes, we use a spray-on adhesive in the layup procedure. We wanted to see if that would negatively affect how the piece performs structurally. The results from this are as shown. The load is on the y-axis, and the bar's height represents how much load the piece can resist before braking. On the x-axis is the label. HT stands for high temp, LT stands for low temp. The addition of G stands for the addition of the spray glue, and the number represents how many layers the piece is. These are preliminary results, and in the chart is about 25 trials. So it basically just compares the pieces between each other. What we found was, as you'd expect, the fracture strength increases as you go up in the number of layers in the laminate. But as we did not expect, the low temperature epoxy consistently performed better than the high temperature epoxy. Also, the spray adhesive had no negative effect on the piece's tensile properties. Further analysis into this data would give the Young's-Montrose and Poisson's ratio, which could be used in an FAA software along with the aerodynamics data to figure out how each piece would perform under loads. So if you were here for the PDR, you saw this image with all of our pieces together. The fins in the fin can are likely going to be purchased again unless we have time to water jet cut them. The motor tube and fins and fin can and the motor tube mount are all aluminum, and we're also going to make our motor tube mount. The transition piece, coupler, body tube, and nose cone, like Anu said, are composite. The coupler, body tube, and nose cone are carbon fiber, and the transition piece is fiberglass, like Anu said. Also, we're going to be using the high temperature epoxy in all of our composite pieces. That's just for heat resistance, just in case the vehicle experiences any shocks along its flight. I'll just do like a brief overview of each piece in general. The nose cone is the same as last year. It's a 27.5-inch bond carbon shape with a 6-inch coupler laid up in one piece. The carbon fiber is 6 layers thick and has an aluminum tip at the top. This year, we're going to add spray glue into the spray adhesive into the manufacturing process. That's just so that the carbon fiber doesn't pull itself away from the mold, and when we actually get the piece out, it'll be the same shape as we'd expect. This worked in test trial, so that's exciting. And also the spray glue didn't have any negative effect on how the tensile properties of the piece. The body tube would slide onto the coupler of the nose cone and meet the nose cone at the shoulder. The length is 31.5 inches. This will also be 6 layers of carbon fiber laid up on an aluminum mandrel. We'll roll on a perforated shrinking tape to squeeze out any excess epoxy and reduce the weight. The bulkheads, this year, instead of using a wood material as the core, we'll use honeycomb. These will be laid up by first making 2 carbon fiber plates, and then after they cure, we'll sandwich honeycomb in between them, along with an adhesive to keep it all together. This piece is our coupler. As you can see, on the end is a flat part where it's closed off, and the top is free, or like hollow. There's no flat plate there. It'll be 10 inches long, and we're planning to overbuild this piece. That's mainly just because where it's placed in the rocket is critical, and it has to adhere the top of the rocket to the bottom of the rocket and experience all the loads and moments in flight. So we can't really confidently make recommendations based on and say it can be 6 layers thick or it can be 8 layers thick. So to add in that factor of safety, we're making it 10 layers thick. And it'll be laid up similar to the body tube on an aluminum mandrel and vacuum bagged. The transition section will be 10 inches long. It'll start at the diameter of the body tube and taper to the diameter of the motor tube. It'll be fiberglass, like Anu said, and it'll be 7 layers thick. This piece is different from last year. Last year, this piece was about 12 layers thick because it was load-bearing, but because this year all of the loading goes mostly through the motor tube mount, this can be much thinner than last year, and that's much lighter. So this is 7 layers thick. It'll be laid up the same as the nose cone on prefabricated molds with the spray adhesive and vacuum bagged. Here's just showing, again, what the integration looks like. You can see at the top is the body tube and where the coupler would slide into the body tube, and the flat face would lay on the motor tube mount. That'll bolt into it, and in between where the transition will bolt in between the motor tube mount and the coupler. Then the body tube will slide all the way over the coupler and be flush with the transition section. So this is our risk matrix for this. I'm calling the composite airframe any composite pieces that are on the outer surface. So that'd be the nose cone, body tube, and transition section. I'm saying the composite airframe, any failure there would result in a catastrophic loss of the vehicle. It's lower likelihood because these are all components that have been flown before and are similar to previous designs, except for the transition section, which was flown before. But if that piece was to fail, it wouldn't cause any catastrophic loss. Similarly, the composite airframe failure due to heating would be if the vehicle experienced any shocks and the temperature increase would cause delaminations in the epoxy or burning. That's a lower likelihood and would cause significant critical impact, but not a catastrophic loss, because it would be a localized failure rather than a whole failure. The coupler failure would be considered a catastrophic loss to the vehicle, and it's in the likely category because we do make this piece and it's at a critical point in the rocket. It's an SRAC component, so you would have any kind of likelihood of failure with that too. The bulkhead and internal component failure, that's kind of newish this year because it's honeycomb instead of a wood. The motor mount failure and the fin failure, because those two are aluminum, they're placed in the not likely category, but would cause a catastrophic loss of the vehicle. And improper integration would be anywhere where it wouldn't be a failure in the piece itself, it would be a failure due to the way it was integrated, which could happen on any piece. To mitigate these risks, mainly the coupler first, we would overbuild to ensure that it's reliable and that it would work properly. For integrated purposes, the torquing of the bolts is really important, and if you torque too far, it could cause cracking. So we're thinking of torquing onto a body tube first to test how far you could, just to make sure that our sources are applicable to what we're trying to do, and the results that we get can be used in what we're doing. Also, we're going to be using fasteners rated for the expected loads. For the bulkhead failure, previously we've been using a laminating epoxy instead of a structural epoxy. This time around we're going to be using structural epoxy to make sure it still gets that adhesion that we're looking for. And also, once we make the honeycomb bulkheads, we could test until failure to make sure that it meets all the loading requirements. For the motor tube mount and fins, basically just ensuring those parts are properly integrated. Like I said before, those parts have been flown before, so the only serious issue would come if we didn't integrate them properly. For the composite airframe, using a high temperature epoxy again for the heat resistance, making sure that once we get the parts completely fabricated, we're checking them for flaws consistently, and then again after and during integration, and also optimizing our procedures to manufacture high quality parts that we don't have to check along the way as much, I guess. Manufacture high quality parts so that we can take certain steps out. And of course, utilizing test launch results and making any changes based on those results. Questions?
Yeah, going back to your coupler, you said that's likely to fail.
Mm-hmm.
So you got to do a lot more testing or do something because likely to fail isn't ready for prime time.
I agree. So we're going to be overbuilding this part to mitigate this risk. We haven't really decided on it can be 6 layers, it can be 8 layers, even though it probably could be. So we're overbuilding to 10 layers. Even though our rocket might not reach 30,000 feet, we think that having under 30,000 feet and not having it break apart would be good.
You're getting loads from the aero people?
Mm-hmm.
Okay, well, that's a red flag. Well, you got the red box.
Yeah.
That makes sense.
Yeah, yeah.
I'm actually glad you put it in the red box. Rest of it, I think you're pretty safe. I still would have liked to have seen that 3 months. Should have built that part at least. I'm more worried about the way you're planning on doing it. The way that the composite's gonna, corners are bad. That's where the stress is gonna happen. I would have really liked to see the building of this, see what it's gonna do. Out for the test flights. That's a crunch time to get everything done. If that doesn't work the first time. How long is it gonna take you to get a part that works? I still think that should be priority 1. I'm glad you marked it as such. Still want to see a part and see when it's going to work.
Sure.
The only other thing I had is you mentioned that you're still going to use the high temp epoxy.
Mm-hmm.
You were showing failure rates lower. First off, why did it fail before the low temp epoxy?
I think that the high temperature epoxy failed before the low temperature epoxy because the high temperature epoxy says to cure in an autoclave, and that's because when the material is laid up, it off-gases volatiles. If you have an autoclave, it uses the pressure to press out all the gas in between the laminate, but atmospheric pressure alone through vacuum bagging, which is what we do, isn't enough to press out completely all the volatiles. So I think that might be a reason why it would be less strong. Yeah, it's up to like 200 or 300 degrees, or
To make an honest recommendation, the entire flight's going to take less than 30 seconds of the averaging. The high heat portion of it's only going to be seconds.
okay.
If you're getting more strength out of the low temp epoxy, you're not going to get enough aerodynamic heat in that short period.
Sure.
Max speed, about Mach 2. So you're not going to get into crazy realms until you get over 2.5, and that's got to be sustained. If you're showing significant strength reduction, that little bit of heat doesn't make any sense. The aerodynamic so low compared to the cost of flight. Unless you're confident that both of them are good.
So,
My gut.
yeah. Yeah, Harrison.
So on for customer failure, you had on the next slide you had shown the different ways of validating it. Two slides. Do you have any plans for just doing like either hand calculations or FEA to validate it along with the physical tests?
We had plans to do FEA. The data that we had used from the composite testing would also go into that. I don't think we'll have those results ready by the time this piece needs to be fabricated. So we're overbuilding this part right now, but FEA in the future for like future versions of the team who want to use this part too would be really good too. Yeah.
What are the loads? What
They're bending and like drag forces. That sounds like a question for Ed though. He's going next too. Yeah. Okay.
I forgot to mention a bit earlier. So as with our PDR, what we're going to do after each section is that we'll have 5 minutes for questions. And if once those 5 minutes are over, if there are additional questions, we'll just have a time at the end of the presentation to ask those. So we have about 1 more minute.
Yeah, I'd say test for torque specification, you need to test for compression, bending, and
Sure. We were thinking it would fail due to torque or, yeah, also due to bending before it would fail in compression, though. So we would do the bending.
That's going to be the force. Not going to get much. Not going to get much. Going straight. Compressing. That's why I worry about that corner.
Yeah.
That's still.
Sure. Okay, I'm going to hand it off to Ed, the aerodynamics lead.
Hello, everyone. My name's Ed. I'm the aerodynamics sub-team lead. And what we do on the aerodynamics sub-team is try to aerodynamically characterize the rocket during flight, which means specifically determining the loads on the rocket, as well as determining stability throughout the flight. And then we also work to improve our members' current understanding of fluid dynamics and potential applications of fluid dynamics. So our requirements as the aerodynamics team are to provide a drag estimate, particularly at the maximum dynamic pressure, which is also known as max Q, which is where the drag forces are highest. We also determine the rocket stability and any potential response to in-flight disturbances. And then further than that, we look to investigate and improve certain rocket components, whether it's the nose cone or transition piece. And then based on those simulation results, verification, and interpretation, we can recommend any potential improvements. We're also always looking to advance the team's simulation capabilities and prediction capabilities as far as the rocket flight goes. And then finally, we are always looking to improve our current members' understanding of computational fluid dynamics, or CFD, which is the software that we use to determine these loads. So our system breakdown is going to be a bit more of an analysis breakdown, as we don't have a physical system on the rocket. But to start, this is our current prediction, which comes from OpenRocket. So it is a slight over prediction, hence why our apogee is right now at 32,739 feet. Our max Mach number is about 1.98. But our rocket is currently stable throughout all of its flight. It is stable off the rail, so that is not a concern as of right now. But of course, it's something that we do always monitor. As far as our analysis, so we also moved into, expanded our 2D simulation from the PDR and updated the max Q conditions to not the most recent simulation, because we only got that most recent OpenRocket data a few days ago, so not enough time to re-simulate everything, but to the most recent one before that, so the conditions are close. And then we also looked at improving our current transition piece, improving the shape of that, as the current conical shape is, there wasn't really any documentation found from our team archives on why that shape was made, why that shape was chosen. So we looked to improve that with a simple convex and concave shape. We also put together an initial fin flutter estimate, and then we have moved into 3D simulations for the whole rocket body to determine an accurate drag representation. And then finally, we're always monitoring stability and trying to better our way or further our methods of stability determination. Oops. So this is the updated 2D simulation, which again is run at max Q. Sorry, these pictures are a little hard to see, but there is, again, like we expect, a shock at the nose cone, a shock at the transition piece, and these are run without fins or fin can, because the simulations are run axisymmetric, which means that it revolves the 2D domain about a chosen axis to simulate a 3D flow field. And so by using that solver, we can't input the fins, because it would just create essentially a block around the back of the rocket and give us inaccurate results. But again, these results are about what we expected, and they will be updated again with the new max Q conditions from the new simulation. Oops. Sorry. So we also looked at improving our transition piece. As I said, there was no documentation on the choice for our conical shape. We began with a simple concave and convex shape, as seen on the right here. These shapes were chosen just sort of as a proof of concept, as whether or not we could actually improve the drag on the rocket, improve the aerodynamic performance of the rocket. We meshed at the same conditions, so it was a larger outer body sizing and smaller inner body, and then a transition layer on the rocket surface to try to capture the boundary layer. And again, we tested these with the same settings in the solver window, which means that we tested at steady and laminar conditions just as an initial simulation to make sure we get results for these simulations. So this is the Mach number, and the results are about what we would expect, where with the convex piece, the shock is more at the trailing edge, which is more of a sharp corner, and with the concave piece, the shock is at the leading edge, which is, again, the sharper corner there. And looking at the pressure results also, these are a little bit more interesting. This is where the drag would be more affected, this is where we'd see the effect on drag would be in the pressure results. And again, you can notice the shocks at the leading edge, or trailing edge on the convex piece and the leading edge on the concave piece. And we also did take drag numbers from the simulations, just as a point of comparison. While these numbers might not be fully accurate, they do provide a good point of comparison when all the simulations are run at the same settings. And so this, with the conical shape, concave shape, they're much higher than the convex shape, so it does bear more investigation, at least, onto whether or not we can improve upon that convex shape and go further from there. We're not currently recommending a change in design, simply because we didn't have enough time to fully simulate and fully validate our results, but it is nice to see this initial simulation results, an initial comparison. And it is a point that we're going to build upon in the future and potentially into next year. So this is the fin flutter diagram. So the equation at the bottom right was obtained from an apogee rocket paper, which derived it from using a NACA technical report. So the lines you see on the graph on the right are different fin thicknesses, where the black line is the simulation data, so it's the max speed of the open rocket data. As you can see, the current fin thickness is the thicker red line, and that is far enough away from the fin flutter, or far enough away from the max speed of the open rocket data that it's not too much of a concern right now. However, this equation is more meant for subsonic flight with higher aspect ratio fins, whereas our fins are a little bit lower of an aspect ratio, and again, we fly at supersonic, of course. So there is more research that has to be done into a better model or a better equation. And then moving into the 3D simulation, so a quarter rocket body was used for the 3D simulation because the rocket can be assumed to be about symmetrical about both axes, which allows us to cut down on computing power needed. We started with a smaller mesh, and by smaller I mean about 3 million elements. And this was to ensure that we get results quicker and sooner rather than later, which we could provide to Carly for the FEA analysis. So a larger outside body sizing again with a smaller inner body sizing, and then a transition layer along the rocket body, and then a smaller surface sizing at the rocket surface. Again, this mesh does need more work. There were issues with the transition layer, with stair stepping is what it's called, where it removes elements where there might be errors around a corner, around sharp edges. So this is currently a work in progress. We don't have results yet from this, but we are currently working on it again. As far as risks to project success go, over and underestimation of drag are fairly likely because it's very difficult to get an on point and exact drag estimate. Underestimation of the drag may induce structural issues. However, our rocket is strong enough or structurally sound enough that hopefully it wouldn't have any real impact on the rocket body. And we're going to elaborate or explore more on this with the finite element analysis and with the 3D simulations. An overestimation of the drag force would simply mean that our rocket might be overconstructed, and then we would not reach the desired apogee. But as our apogee is currently above 30,000 feet, our expected apogee, that is an okay concern for now. Static instability is just means that all that static instability is that how quickly or whether or not the rocket returns to equilibrium after being disturbed. There is chances of that, of course, during flight. You can't predict what's going to happen during a rocket flight. But our simulation data from OpenRocket does provide stability margins. It is stable throughout the flight right now. Dynamic instability is how quickly the rocket returns to equilibrium after being disturbed. That's a little bit harder to test and to predict, but it's not likely to cause significant impact to the vehicle. It can cause damage to the internal components if the frequency oscillations are high enough. So that is, again, something we'll have to look into a little bit more. And then fin flutter can cause the potential damage to the structure of the vehicle, down to the fin can and to the fins themselves, and it can cause you to diverge from your flight path, which would again be reduced apogee. So as far as mitigation of these risks, again, with the over and underestimation of the drag forces, we're going to move into 3D simulations, and that's where we'll get our drag results from instead of relying on the 2D simulations. We can also make our 3D simulations more complex, larger, higher fidelity. And then there's always technique verification and validation, which just means more research, more technical papers, stuff of that nature. As far as static instability goes, we're going to want to compare our data from OpenRocket and our pressure data from our CFD calculations, and that'll give us a good idea of how accurate the OpenRocket data is. And then we could potentially optimize our fins, which would involve, of course, conferring more with Carly and with the new on whether or not that is an acceptable choice. And then as far as dynamic instability goes, the way to minimize that or to mitigate that is to test other conditions during flight, such as directly off the rail, at apogee, at burnout. And also, once you test those, you get the loads and the forces at each test point, and you can, using a stability matrix, you can determine if the rocket is will be dynamically stable, and if those oscillations will return to equilibrium quickly enough. There's also more research that needs to be done on that as far as the team goes. And then as far as fin flutter goes, like I mentioned, we'll want to research more on a better equation, hopefully, that better characterizes supersonic fin flutter. So any questions?
Don't you have any previous data from earlier flight tests, like last couple of years, that you can use for stability?
So as far as previous data from flight tests, we haven't recovered data from our flights in the past 2 years. Last year, we didn't have a flight, really. And 2 years ago, they didn't recover any data from it. So the most recent data we have is 3 years ago, which it's hard to say how how similar that rocket is to today's rocket with the changes that have been implemented since then. So it's sort of, you gotta take that data with a grain of salt.
Have 2 successful test flights that you hold data from. Where is that data?
Correct. So we do have test flight data, and again, we can look at that. It is in our cloud folder. But those test flights only go up to a few thousand, under 10,000 feet, I believe. I'm not sure on the. Yeah, it doesn't. So we can look at those. That is a good point. It just doesn't go up to that Mach 2 that we'll be flying at, and doesn't give us the full range, I guess. So there is more.
Extrapolate your data from your subsonic, if it's matching your subsonic data that you're generating, extrapolate that data that your software is generating for Mach 2 flights is still going to be, I mean, at least give you a baseline that's going to be accurate. Have you compared the subsonic data versus the subsonic that you've done in the CFD?
No, not yet. We haven't really looked at previous flight data, simply because the test flight data, I know there have been a few motor changes too since then.
Well, that doesn't matter, because as long as you got acceleration data, you got accurate masses, everything else.
Okay, real quick, we're just gonna have me run the mic to people who are asking questions. You are gonna use that mic to answer, just so people on the live stream can hear all the questions. So, was that?
I guess extrapolating on that, that's one of my main concerns. Is it's great that you're developing this data, but you've got raw data from several flights, and you should be comparing that to, I guess the word to verify that what you're doing is accurate. I mean, you've got at least a baseline for subsonic portion that you can extrapolate into the Mach numbers that you're talking about for the 30K flight. And I think it's just, don't waste that information that you've collected the last 2-3 years. Also, to answer your question, the reason it's conical, because it was easy to manufacture.
When I had first looked for it?
That would be perfectly fine. And just, because you did show some pretty good numbers there, my highest confidence is with our structures team, just because it's always the largest team and seems to attract people that are really into it. I know Carly's going to have work with that piece that I've been bugging him about for the last 6 months, but because that's a non-load bearing part, I think that's a good place, something to play with, to see if you could manufacture it easy enough.
Yeah, I didn't mention this, but we're also going to look into basing that curve on an equation to make it much easier for them to form a mold or a plug for it.
Can you go back to your risk matrix? first off, you said that underestimation of drag forces and you said you have both underestimation and overestimation of drag forces are likely. Is that you just said don't really know, or is that do you have any reason?
That's because it's difficult.
Subsonic. It's easy to extrapolate the coefficients of drag from the data, even at the low resolutions. This gives you a baseline that shows drag. It's not that hard. Plugging over the number you got, and figure that data, the plane data, and at least get you somewhere in the ballpark to make sure that your predictions are accurate. I mean, it's just, that's wasted data if you're not using it.
Yeah, absolutely. That's definitely something we're looking to do. Yes.
Is there a hand calculation you could do to verify your model?
So we've been using similar CFD techniques for the past few years, and I don't know if there's an exact hand calculation per se. We can look into wind tunnel testing, which is something the team's looked into in the past. Unfortunately, it does involve getting wind tunnel testing time over at the ARC, the Aerospace Research Center here, which is very busy and it can be hard to get access over there. It is something we've contacted a little bit with Dr. Gregory about, who coordinates the ARC. But that'd be the best verification or validation for our numbers.
Did you predict a coefficient of drag?
No, not yet, because we haven't actually produced drag numbers yet. Any other questions? Okay. It's on the board now with the avionics.
All right. Hello, everyone. I'm Gordon. I'm the subsystem lead for the avionics team, which basically is the electronics. So it's exciting. So the purpose for our project is to teach members high reliability and performance electronics through the design of electronic systems that are critical to flight control, tracking, and data logging of the rocket, which is a mouthful, but we'll break it apart as we go along. So some of the requirements and just some of the things that our team is tasked with doing. So primarily is deploying the drogue parachute and the main parachute, and both of those are critical, obviously, to having a good flight. Next is maintaining a telemetry link throughout the flight. Again, that's also super critical because we need to be able to find it afterwards, and those give us GPS coordinates for where to look. One of our goals is to have a quick integration time, so less than 20 minutes is our goal, because we've had issues with integration in the past. And again, that's not super critical, but would be a very big advantage to what we've had to do in the past. Remote arming of all electronics at this point is critical, just with what we have and the technology we built and the way the structure is built. And then recording flight video, again, that's something we really like to have, but is not critical in the complete success of the flight. So we're going to go through with a system breakdown of the avionics system, which kind of excludes the telemetry system, but we'll go over that a little bit later. Okay, so here's our system flow chart, and we're just basically going to go around and break down each section throughout the presentation. So the first thing we're going to look at is the communication system. The first thing we're going to look at is the communication system. If you've been around for a little while, you know we've used this Bluetooth communication system in the past pretty successfully. This year, we're planning to add another component to that, and that is this the central command controller with the CAN bus, which will bring a lot of the parts of the rocket together. So again, as in the past, we'll have 2 Bluetooth modules that manage all the communications from the arm electronics to the rocket. So we'll just have one link in the middle. And these 2 modules will be programmed to pair exclusively with each other. And that was one of the reasons why Bluetooth was chosen in the first place, is because there's a little bit of built-in security there with that these Bluetooth modules are programmed to only pair with each other, and then it won't receive some random noise from just any other signal that's coming along. Then these codes will be sent over a controlled area network bus, or a CAN bus, by the central command controller. So CAN bus is a communication protocol. It's very robust, noise resistant, and one of the biggest advantages is it has an arbitrary number of nodes. So that means that we can continue to add things to this communication bus as the as our rocket technology develops, and with minimal impact on the physical layout of the whole system. You just have to add another node. And it's used oftentimes in automotive, so it's a really robust and relatively safe system. And then these codes will be read by any number of arming circuits, and then actions will be determined by comparing those received arm codes to the ones that they know to turn on or off their specific components. So next we're going to look at the control box side. So we have the control box on the rocket side. The control box is contained separate from the rocket, obviously, and that's where all the arming electronics are. Okay, so the control box, like I said earlier, contains a circuitry that communicates with all the rocket electronics. It'll be 3D printed for a high degree of customization, so we can get exactly what we need. It'll have an LCD screen with a menu, which is something newer this year. It'll have a power switch and then 2 buttons for menu control. And so one of the big advantages of using the screen and the buttons instead of the past, we just use switches, is that it'll be customizable to, you can just update the menu relatively easily just by reprogramming it rather than having to add more switches or actually mess with the circuitry. You just add more options on there. And it also allows to have a positive feedback, so we know when different things have been armed, we can get confirmation that they've actually received the signal and everything. So next we're going to talk about the arming circuits. So they're kind of one of the main workhorses in the middle there. And so they are powering the payloads, the camera arming, and the computers as well. And so we'll dive into how those work. So basically they are going to be receiving signal arm or disarm codes from the central command controller over the CAN bus. They'll take those, and for each individual circuit, there'll be an individual circuit for each component being armed. And then the circuitry, again, will be designed to default on if there's a power failure. So, for example, if somehow the arming circuit fails, there's circuitry built in that will automatically turn it on, which would be a case that we would likely want, because if there was a failure in flight, obviously we would want the flight computers to come back on to have any kind of successful flight. And then also now we'll be able to return a positive response. So you can kind of see we'll have a CAN bus transceiver. There'll be an isolator in between that will isolate that from the rest of the rocket for safety. And then we'll have a microcontroller, a very simple microcontroller, that basically all it does is look for that code, and then we'll be able to turn on the power for its selected component. So next we'll be talking about the flight computers, which are down there. So this year we'll be using 2 commercial flight computers. And so a flight computer, basically, if you don't know, is a microcontroller that detects apogee, which is the top of the rocket path, the rocket's flight path, and then has the ability to deploy the drogue chute at that point. And then at about 1,500 feet above the ground, it'll deploy the main chute. So this year we'll be flying 2 commercial flight computers as independent redundant systems. So what that means is that both of them have separate batteries, separate arming, completely electrically isolated from each other, and both of them can individually carry out the entire mission that the rocket needs. Usually we'll put one in a primary and a secondary role. So the primary one will go off first, and then if for some reason the primary one fails, the secondary one will go off a second or 2 later. That just protects some of the rocket components from the explosives because if you had 2 go off at the same time, it could cause damage. So we have a primary and secondary. It'll be similar to past year's design, so it's reliable. They're commercial flight computers, used a ton, and they're also, we'll be able to reuse some of the parts from last year, which will help on our budget, so that's good. So just the power budget for the flight computers. So we have the stratologger and the telemetrum. So with their current draws and their voltages, for giving a time of 2 hours, which is definitely more than we expect, we should be more than covered with 2-cell LiPo batteries at 300 milliamp hours. So now we're going to talk about the cameras. right down there. So the cameras will be using an action camera to collect flight video. It'll just be simpler. It will basically set up to record automatically on power up. So when they're turned on from the arming circuit through the CAN bus, they'll come on and just start recording immediately. And that'll be nice because in years past we've had to integrate them and turn them on to integration, which usually from the time we integrate to the time we launch can be up to an hour or even more sometimes. So this will be able to do hopefully less than 15 or 20 minutes before we launch. Cool, and now we're going to talk a little bit about the payload arming. So that's a new feature that we're adding this year, or maybe adding depending on the payloads and if they want to use them. But this new communication system allows for easy addition of other electronics modules. So this enables our optional arming for our payloads. So we'll only control the power to the payloads. But basically, the way it would work is that the user would only need to connect their batteries to the circuit, and then they would have to connect the power out to their payload. So it'd be very easy for them to interface with, and then we would be able to manage all of the arming with it. And that would extend their battery life as well, or they could use smaller batteries, which would just build in more security into the system as far as, for things you can't control, like timing delays from integration to actual launch. So we're working on developing a custom flight computer too, which will be pressure and acceleration based sensing, just to get started. And again, it needs to have the ability to deploy parachutes, and obviously it needs to be able to tell the altitude and be able to sense the events going on around it. And then also it needs to be robust and reliable. And so really the reason we're doing this is to enable a higher level of customization on the avionics team and really kind of advance some of our technical experience in that. And two, as we get more custom devices, we can optimize a lot of things, like putting more parts together on single boards and stuff, which saves a lot on space in the future and connections and robustness. And this year we'll fly in a non-critical role for the competition rocket. So it'll be armed in a similar way to the payloads, essentially. So for the bay design, we're designing a 2U Cubesat bay. So you can kind of see that in the left picture here. And so there's a backplane PCB, which is on the back of the green wall on the back of that, which will connect all the modules together. And so one of the advantages of this is that we won't have hardly as many wires running around as we have had in the past. And that we'll talk a little bit more in the risk matrix, but brings definitely a confidence. And then we'll be able to integrate with the payload bay to allow for simplicity and remote arming of the payloads. So you'll see this structure again. This is kind of the system rails that'll be holding the payloads and the avionics bay together. So we'll be able to slide together. The inside parts will be able to slide together, which will be really useful for integration. And then they'll have removable PCB cards, like I said, so we can take them in and out. And then there'll be a securing mechanism to hold them in once we are ready to actually fly. So for telemetry, so these are the electronics that track the rocket throughout the flight. So this year we'll be using a commercial tele-GPS system, which is a commercial system built by Altus Metrum, which makes a lot of different rocket electronics components. So it's about in the 440 megahertz, which is in the ham radio bands. So really what we're using is reliable, easy to integrate. We're familiar with the use. We've used it a good amount. And really just for the ease and all of the other goals that we have this year, we felt that this was one area that we could just go with commercial for that and make it easier. So the telemetry and the battery will be integrated completely into the fiberglass section. Because if you're not familiar, the fiberglass section is RF transparent, whereas the carbon fiber is RF opaque, so you can't actually really transmit very well through the carbon fiber. So it needs to be in that fiberglass section, or the antennas do at least. And one really big advantage of that is in years past we've had issues with trying to get the wires between the transition section and the actual body to the telemetry bay. Well, this year all of that will be contained inside the fiberglass section, so we won't have to worry about that. Which will be a huge integration advantage. And then the ground station will consist of AltOS, which is just the software that goes with this on a laptop. And we have our Yagi antenna for our ground station. So some of the risks to our project success. So we can have, the first two are kind of related, but we have a single flight computer failure or single flight computer battery failure. So both of those are well, especially the single flight computer failure is pretty unlikely because they're commercial products. They're pretty reliable. So I had that in the not likely, but I also had both of those in the minor impact because since we are flying a redundant system, completely redundant, the other one should be able to take over and complete the task. And with the battery, a little bit higher likelihood just because
the battery is a little bit more prone to fail, and also they could die in terms of not having enough power if they are on for too long. CA had as a dual computer failure. Obviously, that's not very likely, again, for the reasons I had before, just that they're commercial systems and they're pretty reliable, but obviously that would result in a catastrophic loss of vehicle, as we would know from the 2018 launch year. And then D, we had a base structural failure. Again, we're feeling decently confident with it because the system that we're using has been used for the payloads for the past little bit as far as the Bay. But again, that would likely end up in the catastrophic loss of vehicle if the electronics were crushed, because again, there wouldn't be anything to control the flight. The camera battery and camera memory, pretty low likelihood, but also those have a very low impact on the actual flight of the rocket. We just wouldn't get video, which would be unfortunate, but we would live. Circuitry failure, again, not super likely because a lot of these are the commercial components, and they'll all be all the systems will be tested, and so we'll likely be able to find those kinds of defects before we're actually about to launch. But depending on what it was and when it was, that could potentially have a significant impact on the rocket. It could end up in catastrophic loss of vehicle, or again, it just depends on what it is. And then wiring or manufacturing error, again, kind of the same boat. Like that kind of stuff we'll catch beforehand because the system won't work if something's not wired correctly. And again, depending on what that is, it could have a significant critical impact. Bluetooth failure or communication error I had as a low likelihood. So we've been using the system for a couple of years now, and it's been pretty successful. And so a little bit lower likelihood, but again, that has a minor impact in the actual health of the rocket. Obviously, it could delay launch or other things like that, but it would not impact the actual flight of the rocket, because once it's going, and that Bluetooth system can't really mess with it. And then the last one I had was a CAN bus communication error, which again is not super likely just because the CAN bus is a very robust and reliable communication system. So some of our mitigations. So again, with the single flight computer failures, really the biggest one is just having the redundant isolated computers, which adds in the extra layer of security. We'll also be able to remote arm close to launch, which should save the batteries a decent amount. A dual computer failure, again, just the redundant isolated computers, and beyond that, that's just a risk you have to take. A base structural failure, we're looking to perform structural analysis for the predicted forces, so just testing that it can actually maintain the amount, maybe with some blank PCB cards to make sure that nothing's getting rattled around, or it's not affecting the way the circuit connections would be if there is force on there. Camera memory and battery capacity, again, the remote arming should solve a lot of those problems, being able to arm it about half an hour or less before we actually launch, hopefully. But obviously, camera memory and camera battery will have enough for about 2 hours of footage. So circuitry failure and wiring and manufacturing failure. Some mitigation is just using our PCBs whenever possible, so that kind of reduces some of those a little bit less secure wire connections and terminal connections between parts, and then circuitry testing as we go along. And then the Bluetooth failure communication error and the CAN bus communication error can kind of be mitigated through systems testing, and then again running as much of our logic and connections through PCBs that are a lot more reliable as far as connection rather than wires and terminals. So with that, does anyone have any questions?
So looks like you got the whole electrical system in here. Question is, the parachute deployment, is that hooked up to the electrical system?
Yeah, so you'll hear a little bit more about that from Rafe later, but basically those are hooked to the flight computers, and when it senses it's the right time to explode those, it lights an electronic match that will light a black powder. So, yeah. Exactly, yeah.
Charges, let's talk about the electrical path coming from the flight computers, charges wired directly to the charges?
It'll be directly to it. So they'll be coming straight from the flight computers. They'll the wires that go directly up to the bulkhead. So the avionics bay sits right underneath the recovery bulkhead. We'll be going straight there. And then we're actually, and Rafe will talk a little bit about this too, we're looking at a connector system to be able to connect that to the wires that are actually in the recovery.
I was just trying, that's what I was worried about, that it was going to be gravel from PC.
Yeah, no, the computers will still be, like, once the computer, like, all the arming, all that stuff is just for arming, and then once the computers are on, it'll still be wired the same way.
So there's an interface there between two subsystems. Who manages that?
I mean, we work together on it, but.
Well, I know.
Yeah,
Who
but.
manages it?
Yeah.
You both manage it?
Like I said, Rafe will be talking a little bit more about the actual interface between like the recovery charges and the computers. So he'll be talking about the actual like connectors and stuff as far as that. But I mean, yeah, he's kind of been taking the lead on that so far. But.
That's one that I had is,
Mm-hmm.
What I'm worried about is what's the contingency, the flight computers, the important things that they use that power.
So basically, as soon as the arming circuits get any kind of power, they immediately turn off the flight computers, and as soon as and it will remain that way until it receives the specific ARM code to turn on the computer. So once those computers are turned on, then it will turn on the computers and it will save that the computers are on, like in a non-volatile memory. So if it does lose power and the microcontroller, the ARM circuit comes back up somehow, it will remember that the computers are supposed to be on. So if that happens, it's like a blip in the power or whatever, it'll come back. There's also I hardwired like analog circuitry, just a pull-up resistor. That if something just goes haywire with the arming circuit, that it should be connected directly to power in order to leave the computers on. And once the Bluetooth system is not paired with the ground station anymore, it won't be able to transmit any signals because all the arming circuits are looking for very specific ARM codes. So even if there's like noise going back and forth on the channel or whatever, it shouldn't be able to trigger like the exact ARM code you're looking at because it's.
My worry is that if flight computers lose power, even momentarily, they go into reset mode.
Yeah.
And instead of the static playing up, all of a sudden they
Yeah. So I mean, I've thought about this a little bit. Even if they were to power off, somehow when they come back on, like they would still hopefully be able to detect apogee, which would be at least the important part.
if they lose, if flight computers lose power during ascent, they're done. They won't work. This is a question they're all asking you out there.
Yeah.
They may not understand a lot of the stuff you're talking about. These are experienced flyers.
Yeah.
They'll hammer you on this.
I mean, yeah, we're going to hammer wherever you're on it. And down to it.
That's why I'm hammering.
So.
If they lose power or cycle even long enough to get them to reset, they are dead pieces. They may as well be out of plastic.
Yeah, I mean, we have a lot of protections against that, but obviously that's always a possibility. I know, I'm ready.
One more. Do you have a mode where you can do a ground test on the system, like go through the sequence of events during a flight?
Currently no.
Telemetry.
Oh, what are you talking? Like, I guess I'm.
The flight computers.
Yeah.
I know that I fly that same computer, so.
So the answer is yes?
The answer is yes.
Yeah, like you can know they're like healthy. Like there are tests that know they're healthy, but yeah.
And the last thing I got is, you might talk to BDL, the guy who designs the telemetry, about extending that antenna some way so that you can pull
Yeah, I thought about that actually, but the only issue is that I could come up with is that the GPS antenna that's receiving is hardwired on the telemetrum. But like I know like we could get this, we could get also extend. I know we could extend the telemetry wires because then we could get the charge confirmation later. But
GPS is gonna work, but the telemetry also feeds you data on battery voltage.
Yeah.
Whether the charges are still connected.
Yeah, that's something we could look into for sure. I know like we're also still concerned about trying to get that integration issue with having the wires go through the transition piece is always a mess. Yeah.
Still an extra safety measure in there.
Are there any questions? Okay, cool. In a minute, we're going to keep going, but first we're going to take a 5-minute intermission so we can get up and get a drink and stretch and go to the bathroom. So it's about 7:45 right now, so try to be back around 7:50, and we'll continue with the presentation then.
Hey guys, we're gonna wrap up intermission and get the second half going. I tried flickering them. I gave my best flicker.
Right now, that way.
All right, everybody, we're gonna get the second half rolling. So if you could please take your seats. All right, well, hey, my name's Joe. Joe Yanoska. I'm the subsystem lead for the Payload project, and we're going to talk a little bit today about the project for Payload. So one can ask is, why do we even launch rockets in the first place? And a pretty good answer to that is payloads, right? Usually we have some sort of mass or experiment or instrument that we want to move to either a higher altitude or, in some cases, even orbit. And so we do something very similar here, right? Our project purpose is to send a scientific experiment to an apogee of 30,000 feet. That's interesting, and it's about 2 to 3 U-sized payload. Additionally, we want to create an effective Cubesat structure. That's the actual structure that holds the experiment and houses it, as well as making an efficient integration method to actually put it into the rocket body itself. And then on top of this, this is an educational organization. So we want to educate our members on, all the aspects of, project design, payload design, and using engineering to solve problems. So a few of the requirements for this project. The main reason we're doing it is because there's a lot of points in the Spaceport America competition actually based in the payload and the experiment that you send up. So that's the main fact. That's the main motivation why we're doing it. So what does the competition define as a payload? Well, they say, so any experiment that you have or demonstration of technology that if you removed it and you replaced it with a ballast of the same exact mass, that it would not affect the apogee, recovery, or trajectory of your rocket. So we're going to really try to adhere to that. Also, they give us an 8.8 pound minimum, so it's important that we hit that. Maybe we have to over-design some weight aspects of the payload to make sure we hit that minimum. And then some more self-imposed restrictions for this project is we want to creatively utilize a rocket launch. A big question that we ask ourselves when we're designing a payload is, could I run this experiment on the ground? If I can I simulate this in a lab? And if we can do that, then what's the purpose of putting it on a rocket, right? So we want to try to think outside the box, think of different experiments that are interesting to send up on an experimental sounding rocket. And in addition to that, we want a simple and timely integration. We don't want to be out there in the field too long. We want it to be simple, don't run into any problems. And then also, there's a lot of other important systems on the rocket, like the flight computer, the telemetry. I don't want to mess around with those before flight or during flight, so I'd like to design something that doesn't have any effect on those. So let's get into the system breakdown. Okay, so the first thing I want to talk about is the Cubesat structure itself. Now this is the piece of the housing that actually holds the experiment together, and that's where the experiment kind of lives. And we are going for a CubeSat design, so this is pretty standard across rocketry. A CubeSat is defined as something that's 10 by 10 by 10 centimeters. And what we're going to be using is this frame you see, and it's going to be made out of aluminum 6061. And essentially all it is 4 rails on each of the corners, held together on the top and the bottom by 2 plates that are cut out. And then it's all assembled together with some screws. So pretty simple. This can also be extended to, you're looking at a 1U right now, but for example, our payload is likely going to be 2 to 3U. So all we have to do is extend these rails to meet those requirements. And then additionally, across the plates on the top and the bottom, we have spaces for threaded holes. This just gives us flexibility when designing our payload, just to let us play around with different layouts and what's the most space efficient. Okay, so moving on to the payload bay, you could say, Joe, that's great. The Cubesat structure looks awesome, but you're just going to slap that into the body tube and let it rattle around? Not really. That's why we have this payload bay. This is the guy that's going to help keep the experiment snug inside the rocket so it doesn't move around during flight. Similarly with the last one, we're working on a previously flight-proven design. So we've flown this kind of design before, and we're just doing little updates here and there to help out with this year's project. So this design allows for simple integration. Really what you're seeing here is the bay itself. All it does is slides into the body tube. So think of like a cup holder and like a cup that just slides really tight into a cup holder, so it's friction fit and you can't take it out. Like the top and bottom bulkheads, and then the circle shape that these brackets make, that is about the size of the inner diameter of the body tube. So this also, like I said again, this will be scaled to, and this should say 4 to 5U, because not only is this going to be housing our experiment, the payload experiment, but it will also have the avionics and telemetry bay inside of that. And then lastly, we're making this out of pretty lightweight materials. So we're going to go for ABS plastic for these brackets. And then the bulkheads themselves, like Carly mentioned earlier, we are moving to a honeycomb core. And that's much less dense than something like wood. So that'll save on some weight. Okay, so that was kind of more like the bones of the payload. Let's get into the science itself, right? So the experiment that we're looking at doing this year is called a vibroacoustic instrument-based experiment system, or what I like to call it is VIBES for short. Basically, the scientific goal for this payload is to use condenser microphones, other instruments that are good for studying vibrations, like strain gauges and accelerometers, to study the acoustics and vibrations that are caused by the motor burn and the aerodynamic turbulence, right? And then kind of see how these affect the vehicle like during launch, and if possible, if there's any way for us to mitigate these. So some big data of interest for this payload is going to be like acoustic intensity. So like how intense is the sound that's being produced. Addition to, we're looking for some dominant frequencies. Because a big thing when studying acoustics are natural frequencies. So like if you have some sort of material or structure, it'll start, if one sound is playing that frequency, then that part will start to resonate at that frequency as well. So say we have electronics that are that have that sort of thing, we want to try to mitigate that as much as possible. So that's something we want to research, as well as how fast the vibrations start to accelerate. And then another thing I want to look at is any strains that are induced by these vibrations. Okay, so here's a bit of a system overview of the payload itself. So the name of the game of these is these condenser microphones over here on the left. Those are a little bit smaller than the one I'm holding right now. They're about 10 centimeters tall and about ½ an inch thick. And we want to orient these, one facing upwards, one facing downwards. One to kind of give a better characteristic view of the turbulence that is experienced near the tip of the rocket. And then one facing downwards to get a really good view of the motor burn. And these will be going into an audio interface, which essentially just takes the analog acoustic information and interprets that in a way that a computer can understand and shoves that over to the computer. These are the audio interface and microcontroller are both supplied power by 9-volt batteries. And then also we are going to have an array of accelerometers laid out inside the payload such that we get useful information and data. And then strain gauges. I'm still in a bit of a design phase for the strain gauges. Right now I'm thinking maybe we have some sort of some test pieces of carbon fiber or fiberglass so we can see how the vibrations moving through those test pieces induce strain. So that gives you a kind of a system overview, really high level idea of how the whole thing, how I want it to work. Okay, so let's talk about risk. So I kind of broke this down into 3 categories. One is CubeSat failures. So this is focusing back on that aluminum structure itself. So say like the frame structure breaks or shears, or say the screws shear, or the experiment comes detached. This will cause shifts around inside the payload bay itself, and we don't want to move around the CG all too much. So we have those down. A is not likely, non-critical impact, and B is not likely, also a minimal impact, because my reasoning there is if one screw shears, there's still plenty of others to hold the thing together. So moving on to bay failures. So again, this is a lot of structural stuff. So we're worried about if the plastic rails, the ABS connectors, the screws that are holding it together, or if the bulkheads on either end, if any of those have some sort of structural failure, that's something that we want to avoid, right? So I have a lot of this I have down in not likely, and so that's all not likely. Like I said, the screws themselves are pretty redundant. Same with the brackets. If one snaps or breaks, there's still an array of other brackets on there that'll hold the structure together. And then the honeycomb failure. Luckily, we have the advantage of there's not too much room, below or above the payload bay. So even if these do break and kind of cause the bay to shift around, we don't give it too much freedom to move around the CG too much. So that's why I have that down into non-critical impact. And then lastly, kind of in their own section is experiment failures. Now these won't cause any, these won't affect the rocket's flight at all, or like the loss of vehicle, because it's all purely science-based. The worst thing that will happen is a loss of science and a loss of data, so we can't do any sort of investigation afterwards. Right, so like a loss of battery, like if the batteries run dry, in-flight cable disconnection. Some of these audio cables that we're working with that kind of interface with microphones and stuff, they can be pretty heavy, so it'll be interesting to see how the forces are affected there with their connection points. And then also a failure to arm and a failure to save data. If we can't arm the payload or if we can't save the data, then in both of those cases we will not have any data to work with. Okay, so here's some risk mitigation. So like I said, a lot of the risk involved in the payload bay is structural. So we can have a lot of so we're going to do a lot of structural testing on this to make sure that it can withstand those high forces. For example, we can do a high load testing where that's just where we apply a lot of weight to the rocket, or sorry, weight to the payload bay to see if it can stand up to that sort of thing. In addition to impulse testing, and that's similar, except that's when you just apply a lot of force at once, very quickly. And to kind of mitigate our arming worries, we are trying a new arming system this year. And so I would like to have, if that doesn't work, at least a second arming method, which traditionally is just opening it up and turning the power button on. To mitigate batteries running out, just have redundant batteries on there. So maybe have one extra 9-volt hooked up and ready to go, just in case one runs dry. Additionally, the 9-volt battery that is hooked up to the audio interface, that runs at a lifetime of 10 hours. So unless we are out on the pad for more than 10 hours, we should not have to worry about losing power to the microphones and audio interface. And then lastly, just to kind of simulate collecting data, we're going to do plenty of dry runs, testing out the microphones, making sure that all the connection points are good and it's actually saving data to the memories, the storage devices. All right, so I'd like to open the floor to any questions.
You showed your subsystem with no connection to anybody else, but the avionics had a wire going to the payload. So it seems like you need an on-off wire from the avionics system.
Yeah. No, I apologize.
And that's another interface that
yes.
doesn't seem to be managed.
Yeah, more of
Structural weight from recovery electronics, anything else?
As far as I know, the recovery is connected to the recovery bulkhead, which is screwed to the side of the body tube. So all the forces should be going through the body tube.
So that's not carrying any of the internal structure on the side of it. Okay.
Yes, in the back.
Where do you think you should put your strain gauges?
Like I said before, this is kind of more an experimental thing I'm throwing into this, because I'm interested in how the vibrations might affect the materials we mainly use for our structures, which are carbon fiber and fiberglass. So right now, I'm thinking of making like test pieces, like maybe some thin rectangular plates out of those materials, and orienting them both vertically and horizontally inside the bay. And that's what we all apply the strain gauges to. And so they'll be inside the inside the 2U to 3U structure.
Can you attach them to the rocket body?
That would be a little bit more difficult because this is integrated right before we launch. So like this whole thing will be selected. If we wanted to attach them to the body, we'd have to find a way to basically attach them to the inner diameter of the body. Oh wow. Yeah, there's.
Do you have a name for your testing plan? I recommend you call it the vibes check.
All right, well, that wraps up the payload section. We'll move on to rate. You can talk about numbers.
Hello. My name is Rafe Sanders, and I'm the recovery lead. And that's the wrong way. So the purpose of the recovery system is to create a system capable of landing the rocket and recovering it safely so it's reusable. We also want to educate our team members on the recovery system while using critical thinking to solve problems. We also aim to research new methods and improve integration and reliability across the rocket and our system. There's three main requirements to the recovery system. First is that the ejection charges have to successfully separate the nose cone from the body of the rocket. The second is that the drogue parachute must maintain the rocket's vertical orientation with the motor down towards the ground. And the third is that the parachute bag must open in a timely manner to prevent tangling while controlling the drift speed and descent of the rocket. A quick system overview. At apogee, the ejection charges fire, releasing the nose cone from the body of the rocket, and this deploys the drogue parachute. At approximately 1,500 feet, the cable cutters fire, releasing the pilot parachute and the main from the parachute bag, and the pilot parachute pulls the main out of the bag. And on final approach, the main parachute is fully deployed, and hopefully the rocket lands safely. Our parachute gores are designed in a MATLAB code, and the MATLAB code is based on several variables, such as apogee of the rocket, the dry weight, and the desired descent rate. It's also based off environmental factors, such as the altitude, the air temperature, the average air temperature, and average air density at the launch site. Our main parachute is a semi-ellipsoidal design, and this year it's about 11.5 feet in diameter, and 4 feet tall. It's comprised of 18 gores. Our drogue and pilot parachutes are much smaller at approximately 2 feet in diameter. The parachutes are made up of 1.1 ounce ripstop nylon, and they use Spectraline for the shroud lines, which are what connects the parachute to the rest of the rocket. The template is laser cut from the MATLAB coordinates, and then we trace this template onto the nylon, cut it with a hot knife, tape the gore sections together, and sew it into a French felled seam pictured here. And that seam allows the needle and thread to make contact through 4 layers of fabric to hold it together. The parachute bag is made of Kevlar, and it's flame retardant to protect the parachutes from the ejection charges. It's about 14 inches tall, cone shape, so 5 inches base diameter, about 4 diameter on the top. The line configuration of the shot cord is comprised of tubular shot cord of Kevlar. It calls for about 46 feet of line. And this year we have reduced the length connecting the nose cone to the main line. This should keep the nose cone away from the other parachutes, such as the drogue and the main, while the rocket's under drogue. And then when the main deploys, it's long enough to still hang about 6 feet underneath the rocket. This prevents tangling and prevents the nose cone from bumping into the rocket on descent. Our ejection charges are modeled in SolidWorks, and we have 2 canisters, one as a primary, one as a backup. This isn't updated. This is not the correct model. We have a different picture of the correct model. Anyway, so the bulkhead, or excuse me, the ejection charges are screwed to the bulkhead, and they only have to be removed for storage or to replace them if damaged. Yeah, and we place 5 grams of black powder inside each canister, and inside the black powder is a nichrome igniter or an E-match, and these are completely sealed to work at higher altitudes. I had some better pictures over here, but the ejection charges are 3D printed with nylon, and the nylon is temperature resistant to withstand the heat of sitting on the launch pad in New Mexico. The wires from the canister go through holes that would be pictured here, kind of similar to what's right there. And these wires connect in one of these 2 ports, and then the other port is the wire that comes up from avionics. And these lever connectors basically create a mechanical and electrical connection. These lever connectors create an electrical and mechanical connection that we don't have to solder a wire that's connected to a live E-match while it's sitting inside black powders to secure it. And they can also be tested through ports at the top right here and one in the back to test connectivity. A quick overview of integration for the recovery system. So the night before launch, we pack the parachutes into the bag. We lay out the shot cords and the D-link connectors. We attach the charges to the bulkhead, and we can even prepare the black powder charges for quick integration. During integration, we screw the bulkhead into the body tube of the rocket, load the black powder, seal off the canisters, connect the wires to the flight computer. Then we put a Nomex sheet down, S-fold some of the shot cord on top of that sheet, put in the parachute bag, then put in the rest of the shot cord, the drogue parachute, and then slide the nose cone on. And the nose cone is secured to the body with shear pins, and then the system is flight ready. This is also an old risk chart. So ignore this. There's 2 main sources of failure for the recovery system. One is ejection charge failure, and in that case, the nose cone does not separate from the rocket, and this causes the rocket to come in ballistic. The other main source of failure is the main chute deployment failure, and this can cause the rocket to come in only under drogue, or under partial main parachute. What should be pictured right about here is tangles from the main parachute, and that is the most likely risk to happen because we actually had some experience with that on one of 10K's test launches last year, and that's why we've redesigned the line layout system. But as you can see, the majority of the risks are associated with catastrophic loss of vehicle, and that's because if the parachutes don't deploy, your rocket's not going to slow down. To mitigate these losses, to mitigate the risk of ejection charge failure, we test the continuity of the ejection charges during integration. To mitigate the risk of lack of force with the ejection charges, we have a redundant charge that has a little bit more black powder. We also conduct ground tests to make sure that they're strong enough to push the nose cone off when it's held on with shear pins. To mitigate main chute deployment failure through the failure of the cable cutters, we again test connectivity during integration. We also have a redundant cable cutter system, so there's 2 of them that fire, and we conduct ground tests to make sure they're strong enough to break through a zip tie. To mitigate the risk of tangles, we've redesigned the line configuration to keep the nose cone away from parachutes. We also S-fold the shroud lines into the parachute bag and S-fold the shock cord into the body tube during integration. And this S-fold allows the lines to unfold like an accordion. To mitigate the risk of tears, we always practice safety and caution during manufacturing. We be careful about where we put scissors and hot knives or anything that could melt or pierce through the parachutes. And to mitigate the risk of fires from the ejection charges, we use fire retardant materials such as Nomex and Kevlar to protect the parachutes from the ejection charges when they go off. Are there any questions?
We can pull them up for you.
I apologize about the slide inaccuracies. We usually use an online program called Buckeye box, and it seems that in the past few hours they didn't update because what I downloaded it appeared fine. So I apologize for that.
I do want to see the charge holders in particular that you design make sense. I mean, everything else is basically the same. The only thing, are you setting up any type of swivels in there? They want any areas?
Yeah, I did not mark the D-links for swivels. I simply marked the knots because this was more about the length of line of fire. But we usually put a swivel right above the main map because the electrical wires have to go up to the cable cutters, and after that it's like, so this usually has a swivel so that they don't wrap back and tangle. Everything else is just D-links, tightening the knots, holding it together.
I would like to see
These are the pictures.
Yes, in the next slide it shows better. I'll let you, we can go through that separately. Yeah, I know that previously you tested this. I'd like to see a little more elaborate testing. Just getting the nose come off is the big thing. If it comes in under broke, it sucks, but in the end, it still comes back safely. Versus not having the nose come off 2 years ago. Makes a nice way in the desert, which sucks. I'm more concerned about the charges. I want to see what you're doing with that sooner than later. Just because that's something that's going to be mission critical. So I know you can sell a parachute together pretty quickly. Let's make sure the charge system for that.
my main thought for using these is if we just used the plastic clips like 30K used last year, you still have to solder that to the E-match unless you use the whole spring system, which we're trying to avoid. So this prevents us from doing dangerous things. Yep. All right, I will move over to Casey.
Okay, good evening, everyone. I'm going to apologize in advance. I suck with microphones, but we'll give it a go. So hi, my name's Casey Ruckman. I'm the propulsion lead for the Spaceport America Cup team. Let's get started with rocket motors, my favorite part of the rocket. So what's the purpose of propulsion? Propulsion's purpose is to research, design, develop, and test a solid rocket motor. That's kind of in the name, right? But also in doing that, we want to give our team members hands-on experience with propulsion systems. So solid rocket motors, like what's creating all of the plume there, but also test systems. So this test stand you see here, and within this metal enclosure, there's a test stand. We also want to work with those test systems because in industry and here, it's very important to test what you do with engineering. Okay, so just a quick overview of some of the structural components. These haven't really changed since PDR, but I'll go over them because I see some new faces. So up here, we have our motor case. This is an aluminum motor casing. It's 98 millimeter outside diameter and 54 inches long. That's what you see on the bottom of the rocket where the fin can attaches to. Right here, which didn't get updated. I don't know why. Either way, it doesn't matter. It's okay. This is a forward closure. This has a pipe on here for measuring the pressure. We don't have that. We just have a threaded hole on the top. That's what we use to ensure the rocket motor gets held onto the rest of the rocket. So when it's descending, all of that, we don't want the forces in the other direction to let the rocket motor fall. So we have a threaded hole there that we put a bolt into, and that's what holds everything together. And that's also our forward seal, so the motor can build up pressure and not explode. Always important. And also we have O-rings and a retaining ring. I know, Todd, this is the wrong kind of retaining ring. I fixed it, I promise. This is supposed to go on the inside. The little notches there, it's the wrong way, whatever. Either way, the O-rings make a seal. We're engineers, we know what those do. The snap rings here go in the bottom inside edge of the motor case, and that's what holds the sandwich of the motor together. Propulsion-specific components, we have the nozzle. The nozzle is machined out of graphite. That's what we use. It's a very temperature-resistant material. Unfortunately, not the most impact-resistant, but luckily, rocket motors shouldn't really experience impacts if everything goes correctly. The biggest factor with these nozzles that we control and have to deal with is this inside throat diameter and this outside exhaust diameter. Those are the two variables we can control to determine how powerful the motor is, how much thrust it's going to produce. And down here at the bottom, here's a picture of a solid propellant grain. This is ammonium perchlorate composite propellant. It's what we use in our rocket. This grain's a little smaller, but it's a similar idea. It's solid composite propellant. So here's a system breakdown. Up here on the top, we have a SolidWorks view of the entire rocket, so you can see the casing has been made semi-transparent. But we have the nozzle with its two O-rings. We have a snap ring down here at the very bottom. We have 8 motor grains in the middle, forward closure, and 2 O-rings. So those broken down and split out into the view here, 8 propellant grains, and so on and so forth. The snap rings are what we're really focused on this year, making sure those stay in. For those of you that know, last year, the rear snap ring failed, or something related to it. So what are the project requirements for propulsion? We've talked about rocket motors. Let's see why they matter to the team. So this year, one of our biggest requirements is to go back to what we know works. Not to drudge up old memories, but so last year the motor did experience a catastrophic failure where the rear closure blew out and the rocket only went 300-something feet, as Avi mentioned earlier. So right now we're going to try to avoid that. So in order to do that, we're going to go back to the propellant mixture that we know worked 2 years ago. We had a motor designed very similar to this, just same. The 2018 mixture was a more stable mixture versus 2019, and we're going to go back to that 2018 mixture, and we really think that's going to help us. With that, we're prioritizing motor reliability goals over altitude goals. I haven't even looked at the altitude, honestly, because I just care about making sure the motor doesn't blow up. As of lately, our simulations show that the rocket is going to go 33,000 feet, 32,000 feet, and that's great. If the rocket does gain some weight, we're not too concerned about it. As long as we don't go below like 20,000 feet, works for me. We're just trying to make it go up. That's the goal, up high. With doing that, And come down. Yeah, that's not my department though. My department's just the up part, okay? So we'll make sure that part goes good. I'll leave it up to all of these guys over here. I trust them all to get it down safely. With that, as I mentioned earlier, we're static testing a lot. So this year we want to conduct at least one full-scale motor static test. So that 54-inch long 98mm motor, we're going to build one, turn it upside down, put it in the middle of the field, and light it, and just see what it does. Take observations of pressure and thrust, and of course, hopefully it doesn't blow up. Those are the three big observations we're going to make. We're going to do at least one of those tests this year. In addition to that, we're also going to try to get back into the Aerospace Research Center. That's a resource on campus, like 5 miles that way. And we're going to test smaller scale motors. They're 54mm motors with only 2 motor grains, so they're pretty small. And the reason we're going to do that, number one, it continues our relationship with the ARC, but also propulsion related, we can develop different formulas that we'd like to try out for future years. This year, propellant's probably not going to change. But if we can gather data that we can use in characterizing future possible formulas, we could always make a more powerful motor or do something else with the motor that just is cool or better to an improvement for the team. And lastly, of course, always going to follow proper safety protocols. There's been a number of high-profile incidents recently with university teams, and if we want to be in the news, we want it to be good. We don't want it to be propulsion related. So we're going to make sure we're following all of our safety protocols, make sure we don't do anything stupid with energetic materials. Rocket motors don't blow up by themselves, but if we are stupid, bad things can happen, so we just want to avoid that. So here's some performance projections from BurnSim. Obviously, we haven't done a full-scale test yet, otherwise I'd be giving you that data. Here's a simulation. Simulations aren't perfect, but it's going to give us a pretty good idea of what's going to happen. So some important results that I want to highlight. The total impulse of the motor, which is essentially the changed momentum that the motor can impart into the rocket, is 19,470 newton seconds. That's a 90% N motor, for those of you that know rocketry. Also, we have the average thrust of the motor, which is going to be 3,626 newtons. For those of you that prefer freedom units, that's 815 pounds. Pretty high thrust. I wouldn't want to be standing on top of that thing when it goes off, but that's just me. 5.37 burn time, 5.37 second burn time. That's pretty quick. I want to see that. I really do. I really do. It's going to be great. And the maximum pressure is 570.7 psi. Last year we were in the 600 range. This year we brought that down a little bit, just try to make sure we don't blow anything up, don't blow anything out. So risks to project success, you can see the 4 of them listed here. So first we have the possibility of a motor explosion or a catastrophe at takeoff or a rapid unscheduled disassembly, whatever word you want to use. It's always possible with rocketry and rocket motors that something could go boom. Luckily in recent years, rocket motors have proven very reliable, especially with APCP. So we don't consider that to be a very likely possibility. However, if that did occur, if the rocket motor did explode, that could damage other parts of the rocket. It could cause it to tumble violently, uncontrollably, because the fin can is on the bottom. So that would be a catastrophic loss of the vehicle if that did occur. Now, I've separated out these 2 failure modes, which isn't normally done. So failure mode B, that's possible, is a rear closure failure. That's what happened last year. So a rear closure on this, the way we retain the motor and the way this motor is designed, the rear closure is, I would say, the weakest point. So that is a slightly higher likelihood of possibility. It's still a low likelihood, and there is still significant risk considering last year the results. We don't fully comprehend why last year happened, so it's still a possibility, but we're confident. C, we have the possibility of an igniter failure. So for those of you that don't know, when you light a rocket motor, or in order to light a rocket motor, you have a kind of like an E-match on a stick dipped in pyrogen. So what we do is we insert that all the way up the rocket motor, up here to the very top of the grains, and when the launch button is pushed, an electric current gets sent, and that causes the element to heat up really hot to a hot enough point where the APCP ignites. There's always a possibility that could fail. It can frequently do so. I had a failure just this past month of an igniter. That was a commercial igniter though. I can't talk, I'm sorry. The igniters we use though are made by one of our advisors, Gary, and they've proven to be very, very good and very energetic. So we don't consider that a possibility. If it does occur, I'm not too concerned because all you have to do is go out there and put a new igniter in the rocket. Easy enough as long as nothing got damaged or the motor didn't chuff too hard. However, that would be a significant non-critical impact because that would delay our launch time. And depending on the standby time of the electronics, that could cause other issues. We might have to come back off the pad and reset up and charge batteries and whatnot. So it is significant. However, if we know what we're doing and we make sure we're watching the time, I don't consider it to be a very critical impact. The last point we have on here is the possibility of insufficient thrust to reach the 30K goal. As of right now, that looks like it's not going to be an issue, so it is a low likelihood of happening. If it does happen, it's not really a big deal. As I mentioned earlier, as long as we get like above 20,000 feet, I'm happy. I really am. We just want to go up high. There is possibility, though, if the motor underperforms from our simulations or if something in the propellant goes wrong, we could always go lower. For right now, it's not going to be as big of an impact as long as we go with sufficient altitude for the parachute to deploy and it comes back down safely. That's all that matters. So how are we going to mitigate these 4 primary risks? For the last one, that's just going to be something we have to watch and keep an eye on with the weights. As our wonderful other sub-teams develop their systems, the weights will change, and we'll just keep an eye on that and see how things go. Like I said, not the biggest concern. The first 3, though, the best way to assure those all go correctly is to just static test the motor. Make sure the motor doesn't blow up, you can static test it. So I mentioned earlier we want to do at least 1 static test, but what's better than 1 test? 2 tests. So we'll test it again. We'll do 2 static tests. When in doubt, if you want to make sure something's good, repeat the test. So after our first static test, if something needs to change, or hopefully not, but if the motor does blow up, we can make changes. If the motor performs perfectly, we'll do it again, make sure it still works. And also in mid-March, we're going to be doing a flight test of the rocket, and that's going to use a smaller motor of the same propellant composition. So that'll be another test of the mixture. It's not the same exact test because the motor is shorter. It has a smaller core to length ratio, which is usually more advantageous. But it's still a test in the motor mixture, so we still include that as being part of our testing. Unfortunately, with motors, there's no real way to do it other than test it. So that's what we're going to do. Just test it, test it, test it. Not done yet. So here's our projected schedule, as I alluded to a little bit earlier. So recently, and I mentioned this at PDR, we've been working on redesigning our test stand and our test stand enclosure to ensure safe operations when we're at the Aerospace Research Center. We've pretty much finished with that at this point. Our next meeting, we're going to finalize that and put it all back together. We made it look all nice, and it should be really functional. So it's going to be great for branding and also more safe. Anything safer is better with energetics. So January 25th to 26th, that didn't get changed. Actually, February 15th to 16th, we're going to try to get into the Arc to test those 2-grain small motors for characterizing future possible propellants. Mid to late February, we haven't found an exact date in there that's going to work yet. Weather is always a big issue when we're going out in the middle of a farm field. But we're going to do our first full-scale flight motor static test. So I'm going to go back quite a ways just to give you a picture, because I really like this picture. That's one of my favorite pictures. We're going to go do that, and I'm really excited for that. So we're going to do that mid to late February, sometime in there. And based on that, we can do another test in mid-March. Let's get back to it, sorry. Okay, in mid-March, we're going to do it again. Like I said, if there's any changes that need to be made, that's the time to make the changes and test them again. And really, hopefully, cross your fingers, nothing else goes wrong. If the first test doesn't fail, which we don't plan it, we don't expect it to, we don't want it to, we think it's going to go great, that'll just prove our results, make sure everything's safe. Two motor tests before the flight is great. It's 2 more than we had last year. That's what I'm going for. Also in mid-March, weather depending, we're going to fly that 4-grain motor using the same propellant composition. That'll be a real test of our mixture as well. And finally, in March to April range, a couple members of the propulsion team are actually going to travel to Dayton. This is new this year. We're going to go observe, help, and work with one of our advisors, Gary, who has done our motor pouring in the past, and we're going to learn the process, and we're actually going to hopefully pour some of our propellant. And that's something new and exciting for the team. We've been trying to bring propellant mixing to campus. We've backed off that a little bit with everything that's happened recently with solid rocket motors, but at least this way we can get involved. I myself am level 2 certified. I'm working on getting some of our propulsion members certified. That's going to make sure we're safe, we have insurance, all that's important, and making sure we're operating successfully and with the university's approval. That's really exciting. I'm looking forward to that as well. Questions?
About ignition of the motor, both static testing and flight.
Okay. I don't have a picture of the igniter on here. That's actually a really great idea. So we use a parachute dipped igniter that when it burns, I don't know how it burns, but essentially it's like an E-match, you know what E-match is. So we have just a stick that we tape it to. As funny as it sounds, it's the best way to do it because it's fall off the motor. But so we just have the stick that's longer than the motor, and we stick it all the way up in the motor, and the head of the igniters rest against the propellant grain, and when the electric current gets sent through that igniter, that's what ignites it and it burns really hot. For flight, we use a stick vertically. For static testing, we'll do the same thing with a stick. Just stick it down to the motor, and we'll just hold it there, tape it there, that way it stays secure.
So it doesn't go through the avionics system?
No.
It's
This
like
is sorry.
SD's rocket launch.
Yes, I did not specify that. The ground control system, either ours or Ezra's out at the site, that will be interfaced and connected to that igniter. So the igniter wires come out of the bottom of the motor. They don't go anywhere near the avionics. Good question. Thank you.
Tell me about how you selected the grain chemistry and the grain configuration.
Okay, so you're asking about why we chose like 8 grains and the specific core diameters that we did?
Well, the burn shape is a function of time of the burning part of the solid.
Okay.
And what's the composition of the chemicals in the grain?
Yeah, okay, I got you. Okay, so the motor propellant we use has been historically developed by Gary, and he's put a lot of work into fine-tuning it and using that motor mixture dozens and dozens of times over the course of years to fine-tune it. With the specific grains, we use what's called Bates grains. They're coated in a special inhibitor that makes it so the motor burn isn't too progressive, progressive or regressive. So it actually gives us a pretty flat line that means we don't have too high of a force on the rocket. That's what really helps us control that burn and make sure we're not going too slow off the rail or just quick and shredding anything. But yeah, specifically 8 grains and the core diameter, those are more so based on just historic practices of what's seen. That's for the simulation to show things work.
It's just an air core, cylindrical core. Well,
Exactly.
So the area is going to increase the burn. So
Yes.
the thrust should get higher. with
Yes,
time.
but so with the way the grains are coated, they'll actually burn, so they'll burn from the core, but they're also going to burn, correct me if I'm wrong, they'll also burn from the ends, and because they're getting shorter, yes, the area on the inside of the core is increasing, but they're getting shorter, so the length of that cylinder, of the specific of each individual grain is getting shorter. So the area is actually remaining relatively constant, not perfectly constant. So there is some curve to it, but it's not like a wild spike like traditional core burners are. But it is not perfectly linear either, like a SD's burner or anything like that. Does that answer your question?
Yeah.
Okay.
But working on there was some talk of nozzle itself. Steve, I'd ask a lot of this stuff just to see where you can take it.
Oh, what?
As I'm curious if you've done anything else on the research side of it, on the things that you can research. I know the formulas.
Yeah. So right now we focus primarily just on a conical shaped nozzle because that's proven easier to manufacture. But that is something we're interested in looking into. I don't plan on flying that on the flight motor this year. However, we did have a capstone team reach out to us in the possibility of doing that with the smaller scale test motors. I'm still hoping they might actually finish that and we can do that. But no, that is something we do need to look into more because if we can get a little more efficient, that's something we can go higher or carry more weight.
So I was a little surprised. What's your height requirement? 30,000 seems to be your goal. What are you required to do?
Okay, so I'll speak here, and if I'm wrong, you can always correct me. So the goal of the competition is 30,000 feet. That's where you want to aim for. And if you don't meet that altitude, you don't get as high of a score. but overall they just look for a flight that goes like near that range. Because rocketry is not an exact science, it's always an estimation. So if we can get as close as possible there, that's always good. But right now we're focused on the priority of not blowing up, really.
That's pretty low bar.
Yeah, it kind of is. But after 2 years of flight failures, the last one being propulsion related, I just want to make sure it works and we get near the range. We've looked at the data in the years past, and last year, if we could have just gotten to like 24,000 feet, we could have taken it in the first place.
Really?
Yep.
Okay.
Yes, ma'am.
And also, there's another, so for the 30K SRAD category, the fact that we try to fly a payload in a Cubesat form is already really difficult. A lot of teams shy away from that because then they can make their fly too smaller and it's much easier to get to 30,000 feet then. So instead, we've been focusing on the opposite of trying to get actual Cubesat structure, which requires us to have a 6-inch ID, like internal diameter, fly to minimum. And because of that, it's so much more difficult to get 30,000 feet, and the judges do recognize that. So in that sense, we could end up doing, like they view that as a higher value as opposed to a team with a smaller,
You get a higher degree of difficulty.
Yeah, exactly. So even if we don't reach 30,000, if we're able to even get even close with that 6-inch fly tube, that already is like pretty impressive, you know? And with the type of motor we're using as well.
So another question, since you had a failure in your previous motor, what have you done to make sure that's not going to happen again? What you're going to do?
So, okay, so in relation to what have we done differently from last year to this year to make sure we don't have a failure. So there's two primary things we've done. First of all, we're going to change the propellant mixture back to the 2018 version. So in 2019, there were some changes made to the mixture, primarily, as far as I know, from magnesium to aluminum, and the size of the ammonium particles was reduced, which typically we don't understand exactly why it happened, but because we made those changes and those we're going to go back to the 2018 mixture, which I don't know how much you know about our 2018 rocket, but that is the rocket that went up to apogee. It just came back down very fast. So the motor did work for that. So we're going back to something we know works. Also, we're going to be doing 2 static tests. So if something does go wrong with the first static test, probably have an oh crap moment. But we'll also, assuming it does go correctly, which we're really thinking it will, that'll be a reassurance that, hey, the 2019 mixture was bad, the 2018 mixture that we have is good.
So you have mechanical failures. It sounds like you're pinning it on too much energy coming out.
Basically, we had too high of a pressure spike to begin with.
Yeah. Can you go back to the slide with the rocket in the propellant sections? You said there was You said there was an 815-pound average thrust.
Yeah.
Does that thrust go up as it approaches that failure snap ring? Right? What does the thrust profile look along the length of the propellant? Because that snap ring looks like it might be bearing a lot of the thrust. And if the average is 870, I want to know what the peak is, because a 5-second burn is essentially a steady state load, right? They usually consider about 3 seconds a steady state load. 5 seconds is more than that. So if you had a failure out the top, you've got a single point failure in that snap ring, and those snap rings are subject to assembly, and they're subject to the corners and how things are machined into that aluminum tube. So I would look highly suspect at that snap ring and how it performs, and if you could add another one, that would be good.
Okay.
Or change the diameter. If you just do the math on the area of the snap ring, I don't know how big it is and what the diameter is and how much you're bearing on that, but you've got whatever I take your peak load, not your average load, divide that by the area and get an idea of how much stress you're putting on that ring, and then figure out what it is. I mean, you've got aluminum wall there that could give way too. So I'm a little suspect of the snap ring in this case.
That's perfectly understandable. So yeah, like you mentioned, the thrust does obviously get generated on the nozzle. That's the point of a rocket nozzle. And that does get transmitted up through the liner all the way up to that top snap ring. And last year, so what failed was this bottom snap ring though, which is a little weird. But so the top snap, so yeah, sorry, this is the bottom of the rocket, this is the top. The top snap ring hasn't failed for us, and I believe part of that is because the way this motor is retained, we have that threaded rod at the top, and that compressive force helps hold that in. But the sheer pressure of the motor last year blew up the snap ring on the bottom. And your concerns are valid, and that's why we don't know exactly why it happened. That's why we are going to do tests this year, or we're going to go back to it and make sure that we know it's a little more stable and safe.
Can you buy a better snap ring?
We use pretty high grade steel snap rings. We have considered the possibility, and I believe we might do this. We're going to test it and make sure. Instead of a snap ring, we'll go to a spiral ring. I don't know the details on how those work exactly, but they will provide a little more distribution because the snap ring doesn't go all the way around. It does have a little bit of gap, so we're hoping that can also help distribute the loads. Did that answer your question at least a little bit?
Yeah.
Okay, so this essentially wraps up our CDR. If you have any further questions, feel free to stay and ask us. We'll open that time up now for that. But for anyone who does have to go now, because I do understand these design reviews, especially the CDR, gets quite tedious and kind of long. But we all are really appreciative of everyone who is either watching it live or staying in the audience and bearing with us with a lot of the technical difficulties we found tonight, as this is the first time we've ever live streamed, but we can only go up from here. So again, thank you all for coming tonight, and if you have any more questions, we'll open that up for like any sub-team too as well.
Right now, the projected date is for the end of March. I'm forgetting the date right now, but it's the second to last week in March.
The 21st. So hopefully by then, but that's really tentative depending on weather right now, to be honest. Not so much schedule, but even that could change. But I've made that a pretty ambitious date, to be honest. So if it does have to change by a week or two, that's kind of in my plan.